right, everyone, welcome back to AI.Code.Cast. We're going to take a deep dive into a problem that I think you're really going to like.
Yeah, this one's really fun.
It's all about finding the longest stretch you can get in a binary array, where you have an equal number of zeros and ones.
Yeah, this is a classic problem, and you see this kind of array manipulation pop up everywhere. Think like you're analyzing sensor data, right?
Okay.
You got these periods of activity.
Uh-huh.
Maybe they're represented by ones.
Right.
And then you've got inactivity represented by zeros.
Okay.
And you want to find like the longest balanced stretch of that.
Okay, so like if my smartwatch is tracking my sleep,
Yeah, exactly.
it can tell me like what my longest stretch of deep sleep is.
Exactly. It's all about finding these patterns hidden within data.
Cool. Okay, so my first instinct is to just like brute force it, right?
Sure.
Just go through every single subarray, count up the zeros and ones, keep track of the longest one.
Yeah, it's simple to understand, right? So it's a lot of times the first approach that comes to mind.
Right, yeah.
Simple. But imagine you have a really massive data set.
Okay.
Checking every single subarray could take forever.
Yeah, it's like trying every key on a giant key ring instead of figuring out the right one.
Precisely.
You get there eventually.
You'll get there, but it'll take you ages.
It's ages and ages.
That's what we mean when we talk about O of n squared time complexity as the data grows.
Yeah.
The time it takes to run this grows so much faster.
Exponentially.
If you double the data, the time could quadruple.
Ouch.
Not ideal.
No, not at all. But at least the space complexity is good, right?
True.
We're not using up a ton of memory.
Yeah, brute force usually has low space complexity.
Okay.
Often O of 1.
Right.
Meaning we use like a constant amount of extra space.
Okay.
No matter how big the data gets.
Right, so it's not really an issue of space, it's an issue of time.
It's a time problem.
Okay, got it. So brute force is out the window. What's a more elegant way to approach this?
Let me introduce you to prefix sums.
Ooh, prefix sums.
It's all about shifting our perspective a little bit.
Okay.
Instead of directly counting the zeros and ones in each subarray, we're going to look at the running sum as we move through the array.
Okay.
But here's the twist.
Okay.
We're going to treat zeros as -1.
Hold on. Why would we do that?
Think of it like a balancing act. We've got our ones. They're pulling the sum in one direction.
Right.
The zeros now as -1s are pulling in the other direction.
Okay.
And a balanced subarray will have a prefix sum of 0.
Okay.
Meaning those forces have canceled each other out.
I see. So if we encounter the same prefix sum twice, it means we've found a balanced subarray.
Exactly.
Bang.
It's like your bank balance.
Okay.
Every 1 is a deposit. Every 0 as -1 is a withdrawal.
Okay.
If your balance is the same at 2 different points in time, it means you spent exactly as much as you earned between those points.
That's a really good analogy.
Okay.
Okay, so it's all about finding those moments where the scale balances out. But how do we keep track of all these prefix sums and their locations?
That is where a clever data structure comes in.
Oh.
The hash map.
Ooh.
Hash map. Done, done, done.
Yeah.
It's like a super efficient lookup table, you know?
Okay.
We're going to use it to store each prefix sum we encounter as a key and the index where it first appeared as the value.
So I'm picturing like a detective's evidence board.
Yes.
Each prefix sum is a clue and the index is a timestamp.
Perfect. So as we go through the array, we're building up this map of prefix sums and their locations. Now the magic happens when we encounter a prefix sum that we've already seen before.
That's our signal.
Yes.
That we found a balanced subarray.
Exactly, because it means we've returned to that same balance as before.
Right.
And since we stored the index of that first occurrence in our hash map, we can instantly calculate the length of this balanced subarray.
Yeah, just subtract.
It's the current index minus the stored index.
Easy peasy. Okay, let's walk through a quick example, just to make sure I'm following.
Sure.
Let's say our array is 10110.
Great example. Now remember, we're treating those zeros as -1s.
Right.
So our prefix sums would go 10121.
Okay.
And notice how we have a repeating prefix sum of 1.
Yep, the first one appears at index 0, and the second one appears at index 4.
So the subarray between indices 1 and 4, that's 0110.
Got it.
Must be balanced.
It brought us back to the same prefix sum.
Brought us right back.
Okay, that's really cool.
Okay.
So we found it without having to check every single subarray.
We did.
Now, how does the hash map help us in this process?
So imagine we're at index 2 in our example.
Okay.
Our current prefix sum is 1. We check our hash map.
Yep.
And boom.
All right.
We see that a prefix sum of 1 has already been recorded at index 0.
So we can tell that the subarray from index 1 to 2 is balanced.
Exactly. And if we continue and we encounter another prefix sum of 1 later on, we would know we found an even longer one.
Oh, very cool. This is so much more efficient than brute force.
Oh, yeah.
It's like we have a shortcut through a maze.
I like that.
Instead of going down every single path, we're using clues to guide us directly to the solution.
I love that analogy.
Yeah.
And speaking of efficiency, let's talk about time complexity with this prefix sum approach.
I have a feeling it's a lot better than O of n squared.
You are absolutely right.
Okay, good.
With the prefix sum and hash map approach, we only need to go through the array once.
Nice.
This brings the time complexity down to a super efficient O of n.
Wow, that's a huge improvement.
It is.
So we're trading a bit of space for a massive gain in speed.
Exactly. And in most cases, that's a trade-off worth making.
Right, for sure.
Now, you might be wondering about the space complexity.
Yeah, how much extra memory are we using with this hash map?
Good question.
It can get pretty big.
It can, in the worst case scenario, we might end up storing all the prefix sums in the hash map, which would give us a space complexity of O of n. But remember, that's the worst case.
Right.
In a lot of real-world scenarios, it won't be that bad.
Okay, so we're generally okay with O of n space complexity if it means we get that really fast O of n time complexity.
Yeah, especially when we're dealing with these large data sets.
Yeah.
The speed gains often outweigh the extra memory.
Okay, this has been eye-opening. I never thought I'd be excited about adding up numbers.
It's amazing how such a simple concept can lead to such an elegant and efficient solution.
Totally. Okay, so we've got a handle on finding those balanced subarrays.
We do.
Using those prefix sums. But what if we want to kick it up a notch?
Okay.
And find the longest subarray that adds up to like a specific target sum?
You're right.
Not just a balance of zeros and ones?
That's where things get even more interesting.
Okay.
But the core idea of using prefix sums still holds.
Okay.
We just need to kind of adjust our thinking a little bit.
Okay, my brain is ready.
All right.
So how do we tweak things to find a subarray with a given sum?
Okay, so imagine you're on a road trip and you want to find the longest stretch of highway where you covered exactly 100 miles.
I'm picturing it.
Your prefix sum in this case would be the total distance you've traveled from the start.
Right, okay.
If at mile marker 200, your prefix sum is 350.
Okay.
And then later on at mile marker 350, your prefix sum is 450. Then the stretch of highway between mile markers 201 and 350 must be the 100-mile stretch you were looking for.
Oh, so we're not looking for repeating prefix sums.
Not quite.
We're looking for prefix sums that differ by our target sum.
You got it.
Okay.
And just like before,
Yeah.
we'll use a hash map to track these and their locations.
So our detective's evidence board is back.
It's back.
But we're looking for clues that are a specific distance apart.
Precisely, we're going to store each prefix sum we encounter in the hash map.
Right.
Along with its index. And here's the key.
Okay.
Instead of just checking for a prefix sum we've seen before, we're going to check if we've seen a prefix sum.
Yeah.
That's our target sum away from our current prefix sum.
Okay. I think I see where you're going with this, but can we do an example?
Sure, absolutely. Yeah. Let's say our array is 1, -1, 5, -2, 3.
Okay.
And our target sum is 4.
All right. Let's break it down.
So we start with an empty hash map.
Okay.
Our current prefix sum is 0. And as we move through the array, we update the prefix sum and check our hash map.
Okay. What are we checking for this time?
We're looking for a prefix sum that, when added to our target sum, equals our current prefix sum.
So like if our current prefix sum is 6,
yes,
we'd be looking for a 2 in the hash map because 2 plus 4 equals 6.
Exactly. If we find that prefix sum in the map, we know we found a subarray that sums to our target.
Right.
And just like before, the difference between the current index and the stored index gives us the length.
Okay, this is really cool. So it's like the hash map lets us look ahead and see if there's a previous point in the array that, combined with our current position, gives us that sum.
It's all about leveraging the information stored in those prefix sums.
Right.
The hash map is just our tool.
Gotcha. Okay, so time and space complexity, are we still in good shape?
Absolutely. We're still only going through the array once.
Oh.
Time complexity is that beautiful O of n.
What about space?
Space complexity is O of n as well. Worst case, because our hash map could store all the unique prefix sums we encounter.
Okay, so same complexity as before.
Yeah.
Which means we're getting that awesome speed boost without using up too much memory.
Precisely. And that's the power of prefix sums.
Yeah.
They let us solve complex problems with elegance and efficiency.
This has been amazing.
It's been fun.
We've gone from that brute force all the way to prefix sums and hash maps to find balanced subarrays and even subarrays with specific sums.
It's amazing how such a simple concept
It really is.
can lead to such powerful solutions.
I feel like I've really leveled up my coding skills today.
I'm glad to hear that.
So thanks for walking me through this.
My pleasure.
Really challenging but rewarding journey.
And remember, the key takeaway here is don't just memorize the steps.
Right.
Understand the logic behind it.
The logic. Yeah.
How you can adapt these techniques to solve other problems.
That's a great point. Thanks for joining us on AI.Code.Cast.
Of course.
Until next time.